So you guys have just had some time to work on this. Let's go ahead and go over this. So for example 2 here, we want to test the following hypotheses at the alpha equals 0.05 significance level, where p is equal to the true proportion of Alzheimer's patients who experience nausea using the new drug. It's still frozen up there, but it's actually not frozen on my computer screen. It's crazy how that happens. Right. All right, you guys have this? Yes? Okay, cool. All right, hypotheses. You set them up as HO is equal to P equals 0.1 and P is less than 0.1. So you have 0.1 or 0.1. Make sure the decimal is clear. All right, assumptions. What are 2 assumptions here for a OnePropZTest test? Randomization. Do we have it? How so? We had a random. It says we had a random sample, right? Of 300 Alzheimer's patients. Okay. Next. Normality. How do we assess normality? NP is greater than or equal to 10, NQ is greater than or equal to 10. Remember, we're using the 0.1 and the 0.9, not the sample proportion. Remember, if you know P, use it. If you don't know P, use P hat. Does that make sense? Yes. All right. What statement should accompany this? There should be a statement after you check. Is this greater than 10? Yes. Is that greater than 10? Yes. Therefore, sampling distribution of P hat. Go ahead and adjust if you didn't say of P hat is approximately normal. I would like you to say that there are at least 10 successes and 10 failures to show that the sampling distribution of P hat is approximately normal. All right. That's an overachiever, but wonderful analysis of your assumption there. So amend what you need to. So far, so good on the first 3 parts of phantoms. Yes? Okay, cool. Moving on. Name of the test? OnePropZTest. Awesome. Time to set up your test statistic. Are you using Z or T? Z, which means we will use what curve? Normal or T? Normal. Okay. So here's your test statistic, P hat minus P over square root PQ over N. So what should go in for P hat? 0.053 or 16 over 300. You can keep it as a fraction if you want. Remember what's going to go in for P? It's going to be 0.1 or 0.10 or 0.10 or 0.1, whatever. And then N is 300. So should get a test statistic of negative 2.69. Does that sound good? What's our p-value associated with that? 0.0035. Okay. This work right here, this normal CDF, I just kind of put that there. You don't have to do that if you use the button in the calculator. Remember, which button are you using in the calculator? Number 5. Number 5 in the calculator. Okay. Make your decision. So you have an alpha level of 0.05, correct? P-value of 0.0035. Is that enough evidence? Do you have enough evidence? Yes, you do. Why do you have enough evidence? Because when P is low, you reject the HO. All right, so there you go. So you're making your decision. You're going to reject HO. So if we're rejecting HO, we are going to conclude in terms of our alternative. So here's your statement in context. Since our p-value is less than alpha, we reject HO. There is convincing evidence to support that less than 10% of Alzheimer's patients experience nausea using this new drug. So I want you to check your stuff. Does it look like this? Okay, cool. Make sure it does. So what's a result of this? So what did we just support? What claim did we support? The less than 10% of patients who experience nausea using this new drug. What was in the stem of the problem? Did you guys read? Well, hopefully not. Because if you take a drug, do you want to experience nausea? Generally not, right? Do we have that? We have less than 10%. What's the manufacturer? What do they claim? Yeah. Yeah, it's less than. So this appears to be true, correct? Because we just statistically proved it that it's not 0.10, it's less than. So the manufacturer said it's less than. We proved it's not that in favor of the alternative. So yay. We're happy here. Alzheimer's patients will not have nausea when taking this new drug. It's not likely to happen, right? Okay. You guys good with checking your answer? Questions? Do I need to leave the screen up here for a second? Nope. All right, so we need to go to the next part with interpreting a p-value. Now, to interpret a p-value, remember, a p-value is the evidence you have against the null hypothesis, assuming that that null hypothesis is true. So what that probability really means is, if your true proportion or mean is exactly what you say it is, if it's true, then there is a p-value % chance of observing the sample proportion or sample mean as extreme or more by random chance. You guys remember I was talking about the joy activity yesterday? By random chance, she got 11, well, we hope not, but she got 11 out of 12 shirts guessed correctly. Quote unquote guessed correctly. She actually knew what was going on. What's the probability of observing somebody guessing 11 out of 12 shirts or more by random chance? Do we have anybody in this classroom who guessed 11 or more correct? No. That's the probability of observing someone who gets 11 or more by random chance. That's a p-value. That's what we're saying. We observed Joy get 11. No one else got 11. So that was 0 out of 28. There's a 0% chance by random chance that she did that. Okay? So when you're taking these samples, you're talking about that. There is a blank % chance of observing whatever you saw in your sample or something more extreme, and that goes in the direction of that. So in our context here, remember, what did we say was true? What is our null hypothesis? If the true proportion of Alzheimer's patients who experience nausea from this medication is really 10%. So this is assuming that HO is true. So this statement right here is assuming that HO is true. So if you assume here that HO is true, then there is a 0.35% chance that you would observe 16 out of 300 or in the direction less patients who experience nausea by chance alone. Do you guys see that this was the p-hat right here? Yeah. It's p-hat. This is your p-value. This is your probability, right? Lower was because of the direction of HA. Remember, you were testing the alternative hypothesis here. The p being less than 0.1. You guys remember that? That's why it's this or lower by random chance. Okay. This is something that you guys often struggle with knowing. So I really want you guys to make sure you know how to do this. What does it mean for a p-value when you interpret? Assuming the null is true, there is this much chance of observing your sample proportion or your sample mean being that extreme or more extreme by random chance. More extreme doesn't always mean higher. More extreme in this case is lower. And how do you tell the direction? You look at the sign of the alternative hypothesis. That's how you do it. Cool. Nice. I love second period. So enthusiastic. Love to talk to me. Okay, yeah, cool. Thanks for it. All right, I'm just going to move on. Okay. All right, we're going to do this one quickly together. According to the Center for Disease Control and Prevention website, 50% of high school students have never smoked a cigarette. But they have smoked a Juul, right? Just kidding. All right. Jenny wonders whether this national result holds true at her high school. So what does Jenny do? She takes an SRS, a simple random sample, of 150 students from our high school, and 90 of them have said they have never smoked a cigarette. Is there convincing evidence that the proportion of students at Jenny's high school who say they have never smoked differs from the national proportion? I don't know. Guess what we're going to do? We're going to find out. So we're going to do a hypothesis test. Oops. Spoiler alert. There are at least 10 successes and 10 failures. What do we want to test here, folks? We want to test the following hypotheses at the alpha equals 0.05 significance level, where P is the true proportion of students in Jenny's high school who would say they have never smoked a cigarette. Get to writing. I know. I know. I have to write. It's awful. So our hypotheses here are going to be P is equal to 0.5 because that's the national proportion. What's going to be the alternative if we want to figure out if it differs from not equal to? So HA is going to be P is not equal to 0.05. Or 0.5. Not 0.05. 0.5. Remember, there are two assumptions that we must have for a one proportion z-test, correct? First one is we do have a simple random sample of 150 high school students. And we must check that normality. So NP, NQ greater than or equal to 10. So 150 times 0.5 and 150 times 0.5 is going to be 75 in both cases. So since 75 is greater than or equal to 10, there are at least 10 successes and 10 failures. All right, you guys good with those assumptions? Yep. All right. What are we going to name this test? One proportion z-test. Very good. Remember, that's going to be number 3 on our inference procedure board. What's after N? T. We need to calculate our test statistic here. What's P hat going to be? 0.6. Very good. What is P going to be? 0.5. So then you're going to go set it up in your little formula there. And spoiler alert, you're going to get negative 2.4. You guys need to see it, show me, or do you need me to show you how to type it in? Do you need a recap and going to the buttons and pressing all the buttons? So I can do that for you. You do? Okay. All right. All right, so from calculator screen, go to stat. I'm going to go over to tests, and then we're going to choose the one that says one proportion z-test, which is going to be number 5. Enter there. Okay, remember P sub 0 is going to be the proportion that you use within your hypothesis. What's the proportion we use there? 0.5, right? Or 0.5. How many successes do we see? 90 students, right? Out of how many? 90 out of 150. All right, are we doing, which way are we going? Less than, greater than, not equal to? Not equal to, so we're going to keep it where it is. We can go ahead and calculate, and boom, there you go. So you have a z-statistic of 2.45 and a p-value of 0.0143. Right. Now notice here that in my PowerPoint we have negative. It doesn't matter because remember that you can double this area and you're going to get that 0.143. Okay. Actually, I think this should be positive anyways. So let's just make that positive. See, there was never a negative sign there anyways, correct? You guys didn't see that. I don't know what you're talking about. It's not there. No, you cannot see it. You are lying. You are lying. It's okay. No, we're not rewinding anything. Yeah. Nope. Okay. All right, so here you go. So what do you think about this p-value? Is that enough evidence? All right. When I ask you if it has enough evidence, what I'm asking is the p-value low?
Yes.
Is that enough evidence? Yes. Okay. If the p is low, you have enough evidence. That means that assuming that 50% have never smoked a cigarette, assuming that 50% had never smoked a cigarette at Jenny's High School, there is a 1.43% chance that we would see a sample proportion of 90 over 150 or something more extreme by random chance. It's pretty unlikely. So if that's pretty unlikely, we're going to reject the null in favor of the alternative. And we're going to say, hey, our p-value is low, so we're going to reject the hoe. So there is convincing evidence that the proportion of students at Jenny's High School who say they have never smoked a cigarette differs from the national proportion, and that's that national proportion of 0.5. So here, since our p-value is low and lower than 0.05, you're going to link it, and you're going to reject HO, and you're going to say that there is convincing evidence here that the proportion of students at Jenny's High School who have never smoked a cigarette differs from that national proportion. Now, unfortunately, this doesn't give us a lot of whereabouts. The only thing we were able to say here is, hey, it's not the national proportion. It differs from 0.5, correct? That's all we were able to say. So my question is, we know it's not 50%, correct? We know it's not 50%. So is it higher than 50% or is it lower than 50%? The true proportion of students at Jenny's High School who have never smoked a cigarette. We know it's not the national proportion. Our high school, is it higher than that who have never smoked a cigarette? Or is it smaller than that? Guess how we can find out? We can do what's called a follow-up panic, correct? So what we're going to do is, we're just going to do the Nick part, though. Because haven't you already defined the parameter? Yes. Haven't you already stated the assumptions? Those follow suit from the panic, right? So what are we going to do here if we're going to do a different procedure to estimate where the true proportion is? A one proportion Z interval. And we're going to do that with 95% confidence. Anybody want to know why we chose 95% confidence? Because the alpha level is 0.05, and that's 5%. So there's a relationship there between the significance level and the confidence level you can use. They happen to be complements. So for instance, if we had a significance level of 1%, what confidence level would tie with that? 99. If we had an alpha level of 10% or 0.10, what confidence level matches with that? 90. Does that make sense? So they happen to be complements there. So we're going to do a 95% confidence interval for this. Lucky for you, you have already all this typed into your calculator. You just have to go press a different button. So let's go press that different button. So let's go to stat. We're going to go over the tests. And then you guys remember the one proportion Z interval? Where is that? That's an A, correct? Notice that all that's already pretty much typed in there for you. Isn't that nice? So we're going to go quickly do an interval. And there's where we think the true proportion of students at Jenny's High School who have never smoked a cigarette lies. Where do we think it lies between? 0.5216, 0.6784. So is it higher or lower than that national proportion? So do I need to go back? Okay, so you go stat, you go over the tests, and we're going to go choose one proportion Z interval. So we're going to go all the way down to A. Enter. Change that to 90, 150, and 0.95. Right? All right, so let's go back. And we've got to actually show the work that we did. So here's the work. Correct? The work. hat plus or minus E star times square root P hat Q hat over N. Remember, for intervals, you use P hat instead of P because you're estimating it. You don't know where it is. Everyone okay with where the 1.96 came from, too? It's that memorizable Z star you should memorize from last chapter for 95% confidence. So 0.6 plus or minus 1.96 times square root P hat Q hat over N. And then we already got that from the calculator. So how should we conclude this? We're 95% confident that the interval from 0.52162 to 0.6784 captures the true proportion of students at Jenny's High School who say they have never smoked a cigarette. And when we're comparing that to the national average, what do we know about that? It's higher. It's higher than the national average. So Jenny's High School specifically, we believe her national average at her high school, or the, not national average, her school's average is higher than the national proportion. I should not use the word average. The true proportion at her high school is higher than the national proportion. Because that entire interval is above what? 0.5. Notice that if the interval is above that or below that, you're going to reject HO in that case, which I think is interesting. Later on in Chapter 9 and a little bit in Chapter 10, we'll talk about using confidence intervals to make decisions about hypothesis testing. So if you have like a P equals 0.5 and your confidence interval doesn't contain it. You guys remember when those values did not contain within the interval? If the values were outside, that means you would reject HO. And if the values are inside, you would fail to reject HO. So that's an interesting little tidbit that we're going to continue. All right. You guys good? Questions, comments, concerns? Yeah, of course. It's my parting gift to you. Homework. You know, that thing I used to like punish you guys with practice. Homework is out of love, though, I promise. It is. I know you don't believe me, but... All right, tomorrow we are going to talk about one sample t-testing and compare that to the tests and procedures we already know.